Okay, in this example, we will look at the Fourier transform of Dirac delta that is functional and denoted by Dirac of t. It can be shown as arrow at origin. Here 1 is the area under this Dirac functional. In fact, it is not a function, although Dirac delta has no physical meaning. Its mathematical properties make a lot of things easier when the function interacts with other functions. To derive the Fourier transform of this Dirac delta functional, let's start with the definition of Fourier integral. In the Fourier integral, substitute x of t by Dirac t, and here we need to use a property of Dirac t, that is shifting property. In the shifting property of Dirac, integral from minus infinity to plus infinity, Dirac t f of t dt is the value of f at 0, because the argument of t equals 0 is defined for Dirac function, so we just substitute this argument in the f function as a result of integral. So using this shifting property, we can easily see that the result of this integration is e to the power minus j omega 0, and that is 1, constant 1. And plotting this Fourier transform, we get constant 1 for all values of omega. And this kind of Fourier transform has applications in communication systems, such as white noise has such a constant spectrum for all frequency values. Okay, now let's take a look at the problem if Dirac delta is defined in frequency domain. That is, x of omega is equal to 2 pi Dirac omega. That is, if we plot this in frequency domain, that is arrow at origin with magnitude 2 pi. In fact, this 2 pi is the area under the Dirac delta. And taking the inverse Fourier transform by writing the inverse Fourier transform integral, that is 1 over 2 pi from minus infinity to plus infinity, and in this integral we substitute x of omega by this Dirac function here, 2 pi Dirac omega. Again, using the shifting property given above here, this integral result is 1 over 2 pi times 2 pi e to the power j0 t, and that is constant 1. So plotting this function in time domain, xt is constant function with value of 1 for all values of t. So by looking at these four figures, we observe a symmetry here, and Fourier transform of Dirac t is 1, and Fourier transform of 1 is 2 pi times Dirac omega. And from this example, I want to point out the duality principle of Fourier transform. That is, in general, for a given function x of t, lowercase x of t, the Fourier transform of this is capital X of omega, and if the time function is capital X and just the argument is t, in this case instead of omega, if such a function is given in time, the Fourier transform of this function is 2 pi times lowercase x minus omega, and this is called as duality principle of Fourier transform, and it is very nice property and make life easier to guess the Fourier transform of dual functions.